Istituto Superior, no, Universidade degli Studi dell'Aquila. Yeah, okay. That's my best. And he'll tell us about Virial inversion and derivation of density.
Okay, so thank you very much. It's a great pleasure to be here among so many friends. Since a long time. So the goal of the talk is about, as in the title, is about Virial inversion, Virial expansions in particular, or more, let's say more general, is about the rigorous derivation of, let's say, equations of state. So what do we want to do in statistical mechanics? So we have an atomistic system. We want to tune the microscopic parameters and define macroscopic laws for the quantities of interest. So we would like to have a rigorous derivation of equations of state, which describe the behavior of these macroscopic parameters, or let's say derivation of thermodynamic functionals, free energy functionals, weak energy functionals, etc. Whatever is needed in every specific problem. No, different problems, we want to study free energy functionals, in other we want to study correlation functions, depending on the problem. Of course, this is a very hard thing to do, rigorously at least. And we would like somehow to understand what is the underlying framework and what we can do rigorously, what we cannot do rigorously, how maybe we can implement numerical methods in order to make simulations work better. So this is the general framework. Okay. So these are very general goals. So what is the starting point? So the starting point is we are in the classical system. So we have a box, lambda, of particles which are not necessarily on the lattice, they are in the continuum. And particles are represented by positions. So let's say we have positions q1, qn, we have a number of particles, and they interact via perpotential. So this system is described, for example, by the canonical measure. So I start with very, very general material in order to set up what is the problem. I mean, the problem itself is very, very basic in some sense, even though there was not a proof, but okay, so I start with this very basic stat mech course, if you want, crash course, but I need it in order to explain the problem. So the canonical ensemble, it's just given by the partition function, which integrates over all possible states of the system. So I integrate over all possible positions dq1, dqn in the box. And I have the Gibbs weight for each one of the configurations, which is given by e to the minus v, and I have a perpotential. So whatever I'm going to discuss is valid for perpotentials. Some of the results are valid for multi-body potentials, but in order not to enter into the details, I consider only perpotentials. And so this is the canonical. So this is the Hamiltonian that gives the energy of the system. So if you are in zero temperature, people tend to minimize the energy of the system in order to find the behavior of the material. But if you are at positive temperature, then the entropy plays a role, which comes from this fact that I have n particles and I have to integrate over the phase space. So some energies might be lower, but might be realized by less configurations. So there is a competition between energy and entropy, which is recorded in this partition function. So all thermodynamic properties of the system are recorded here. Okay, so this is the canonical description, which is based on the fact that I have fixed the number of particles, but there is also alternative and equivalent description given by the grand canonical, which is just letting the number of particles be free. So I have a partition function. Of course, this depends also on the volume and depends also on beta, which is the inverse temperature, is the one which controls the competition between the energy and the entropy. So the grand canonical ensemble, instead of fixing the number of particles, I have a Lagrange multiplier of all activity, which is essentially controlling that. So it gives a weight for each. So I have a sum over all possible number of particles. So 1 plus the sum from n to infinity, and I have z to the n times the canonical partition. So I apologize for all of you for this is so trivial and well known, but I said I have to start it. Okay, so these are two equivalent descriptions of the system. And as I said, we want to derive equations of state, free energy functional. So this is a calculation known since a century now, not 80 years, let's say. And it's the following. So what people would do is we say we are in some dilute regime, so close to the gas phase, dilute regime. So this goes back to Mayer in the 40s. One can write down that this is an analytic series. So how shall I do this? Okay, so one of the quantities that might be interested, I might be interested macroscopically is the pressure. So I write it in a finite volume. So the pressure would be defined by 1 over beta lambda, 1 over the volume, the logarithm of the grand canonical partition function. And this nice trick by Mayer was the fact that could compute the logarithm to this partition function, and it's a very nice and simple calculation based on the following observation. So let me write the partition function. So this is the logarithm. So the partition function is, let me say, the sum n bigger or equal to 0. I start from 0 in order to include 1. And then I have z to the end, and I write the partition function, so over n factorial. And I integrate this. So the Mayer trick consists of the following: to take the integral dq1 dqn, and the sum, I make it a product. I add and subtract 1 of the product I smaller than j of 1 plus fij, where fij is by definition e to the minus the potential xi xj times 2. Okay, so what I did, I added, I subtracted 1. I brought the product of the sum outside. I added and subtracted 1. I have the nice form. So the product of 1 plus f, I can expand it, and I can write it as a sum over graphs. Okay, so it's very easy to convince yourselves that this product will be the sum over all possible graphs on n vertices. Right? Because I will take the ones, then I will take only f's, then I take products of f's, 2f's, 3f's, 4f's. So each one of them would correspond to a link in a graph on n layers. So for example, this graph would be f to 3. Okay. Now the nice observation of Mayer is that if you can do that, then you have the logarithm of the sum of this object, which is like in combinatorics, you can think as being the generating function, because it's given as a power series of z to the n over n factorial, of an object, which is like the weight of a graph. So I have the generating function of all graphs, which are not necessarily connected. It's a one-line calculation, formally, to see that the logarithm of this object is essentially equal to the sum of all graphs, but which are connected. From 1 to infinity, of exactly the same object, where now the graphs are connected. dq1, dqn, small n, the sum over all graphs, let's say in connected graphs. The product of f's. The idea is very simple, because if I take here any disconnected graph, so if I take any graph here, which looks like this, then this is essentially a partition of connected graphs, and the partition is an exponential, the log goes with exponential, and they get the sum over all in connected graphs. Okay, so this is the proof. Which is nice, because now I was able to write down the pressure, and to prove that maybe under some regimes where this power series is convergent, that this pressure is an analytic series, with which I can do things I like. For example, I can take derivatives, I can investigate the phase diagram. Of course, the regime that I'm interested in, which is the regime where phase transitions occur, is exactly the regime when this stops being an analytic function. And this is where this method fails, and that's why I do it in dilute regime. Of course, in real experiments, in chemistry, etc., this is not the interesting regime, right? The interesting regime is when phase transitions occur.
So by dilute regime, you just mean
In this
converges.
low zeta, small activity.
Yeah, but just to make sure that the series converges, or
Yes, to make sure that the series
that's the
converges.
condition.
The standard definition for the validity of the micro expansion. Exactly, that the series converges. And this converges in this part. I mean, there are many series depending on the regime that you are looking at. So you might do low temperature, high temperature. There are different things. But in this format, this is our perturbation around the ideal gas essentially. So I consider this are small. So it's a perturbation around the ideal gas. So this is true for small z, for small activities. Okay. All right, so this is about the pressure, but I can do the same thing also for the free energy. So there are two ways to do the free energy, because I said not to write free energy functions, right? So this is the goal, and later on I want to do it for more complicated systems. So what would be, if I want to write the free energy with respect to the density? So I write what the density is. So the density, microscopically, is the expected value of this Gibbs measure to find a particle at some position. So if I write this expected value with that Gibbs measure, it turns out that this is given by z times the derivative with respect to z of the pressure. It's an immediate calculation to see that the density is given by this. So okay, that's not a problem. This is an analytic function. In terms of z, I can take the derivative and I can compute that. Right? So if I want now to write the free energy, so I need somehow to invert this. So say this is a power series in z. Is the power series with the same radius of convergence, because this is an analytic series. The derivative has the same radius of convergence. So this is an analytic series with the same radius of convergence. And maybe I can invert it because the first term is constant. So let's say that I'm able to find an inversion. That I write the activity as a function of the density. Okay. So the virial expansion is exactly that I take this activity and I plug it in the expression for the pressure. And I write a function pressure of, where now I put the activity as a function of rho lambda that I got from here. And this will give me the equation of state. The pressure with respect to rho. Okay, so this will give me rho lambda plus higher orders. Okay, so this is the equation of state where P equals rho is the equation of state of the ideal gas, and these are the higher order corrections made by Mayer around the 50s, the 40s, 37. Mayer and collaborators. So now, so this is the equation of state of the non-ideal gas. The ideal gas is the first term. And these are the corrections, and this was a big revolution in chemistry, that people were doing that, and that by that time, if you read the papers, they tend to believe, which is wrong now, that this could be valid up to the transition, phase transition point, which is not the case, because these things stopped being analytic much before. I will discuss about the radius of convergence later. Now, the point is that here, this was a formal calculation. Mayer did not care about convergence. So it took like 25 years, and then this has been made rigorous by Lebowitz and Penrose, Oliver Penrose, 64, where they proved that this series action is analytic. Okay, this, the fact that you invert and you plug it in. Penrose, a couple of years before, proved that this is analytic by himself, and then Lebowitz and Penrose proved also that the Virial expansion is analytic. 64. In the previous papers, these people had some discussion about whether they are convergent or not, but there was no proof. A big breakthrough was done by Penrose when he proved somehow that this kind of graphs, because initially you see these graphs are graphs over n vertices, so they are e to the n squared many, 2 to the n squared, because I can put or not put a linked graph. I have two options in as many pairs. So the pairs on n vertices are n squared, so I have 2 to the n squared. So 2 to the n squared is something which is not convergent, right? So Penrose proved that actually these are not 2 to the n squared, they are 2 to the n because they are as many as the trees, because there are many cancellations, and this helped for this to be convergent. Okay. All right, so this is the story of the Virial expansion. And in fact, this now we can do it also directly. We don't need to invert it. In fact, one can directly work with the canonical partition function and write it in terms of the density. Because before what one would do, so this is, let's say, the grand canonical pressure. So the grand canonical free energy, let me write it like this, is the free energy, and I write grand canonical to distinguish it from the canonical, would be the Legendre transform of this pressure. Right? So the grand canonical by thermodynamic principles is the supremum over Z of rho lambda log Z minus P lambda of Z. So if I compute this supremum, so if you compute this supremum, you find immediately that this is this density here, right? Because the derivative will give me rho over Z equals P prime of Z. Is this? So if I plug it in there, I would find an expression for the grand canonical free energy, which is the one realized at the supremum. And one could do that also in the canonical by working directly with the canonical partition function. So let me say F and then distinguish it with the canonical, which is now minus 1 over beta lambda, the logarithm of the canonical partition function. And in fact, you can write that this is a power series in density, and in the limit, as lambda goes to infinity, is the same with that, only the thermodynamic. So this was not known for some time. I mean, people believed that to do the cluster expansion, you need to have the infinite sum in the grand canonical pressure. But actually, we were able to prove it with Virial and myself in 2012, I think, that this cluster expansion actually holds in rho, but unfortunately, we had the same radius of convergence, we could not improve. Okay, so this is the background material. Okay, so this is the candidate for the free energy functional with respect to density. Okay, that I was talking about before. Okay, so somehow this is example 1, the homogeneous case. So this is starting point, example 1. So allow me to say here example 1, and I call it homogeneous case because density is constant. Right? I have the particles, the density is constant. And the degrees of freedom are just the position of the particles. Now let's say we want to work with liquid crystals or more complicated systems. So example 2 would be the inhomogeneous system. Inhomogeneous system. And in principle, now we have internal degrees of freedom, internal degrees of freedom. For example, shape of the molecules, orientations, and whatever you want to use for more complicated systems. So somehow she doesn't like you bring this down. I keep it here, but I'm not told. I'm sorry. So I will try to find a way.
No, what you can do.
Okay.
You can put it up. The other
I
way
put
around.
it up. Yes, you see, you have to be smart. There's no need to be tall. Good. Okay. So example 2 is this, and in order to do this example 2, let's do what Onsager suggested maybe. So to have simple, to have a specific example, let's do Onsager's calculation. Onsager's calculation in 49 for liquid crystals. For liquid crystals. So he did exactly what I did before. Okay. So, but now he added orientation. Okay, so we have internal degrees of freedom. So now we don't have only a position of a particle, but we have a particle with some orientation, which is the orientation of so we can think of a rod, of a long rod, and this rod has position and orientation. So, of course, we would like to have continuous orientation. And he said, okay, let me start with discrete. So I discretize all possible orientations on the sphere. So let's say, and then he considered each different orientation as a species. So discretization of orientations. And each orientation, he considered it as a species, a special species. So let's say orientation AI, this is the angle AI, I use the letter he used to use, is corresponding with a species of population n. Okay, in such a way that the sum of an I is equal to n, which is the number of particles that I have initially. So we have a multi-species system, each species corresponding to a given orientation, and he wants to do exactly the same program. So it's not difficult to believe that for finitely many this can work. Okay. Of course, he works in the canonical ensemble. He doesn't work in the grand canonical ensemble. He does that for a fixed number of particles. So let me just write for completeness the form he has. So he says that the logarithm of the canonical partition function, can be for multi-species is a simple generalization of what you get for the one species. So the formula he has is now I have many species, so I have to sum over all species. Let me say k, the number of particles. So this will be the density times 1 plus the logarithm over n k over the volume. And then I have higher order corrections, n squared and cubed, but n squared will be products of n k. So plus 1 over 2 times the volume, sum over k1, k2 of nk1 and k2, and there are coefficients of which depend on the orientations, ak1, ak2, plus higher order terms. So in the limit that n goes to infinity, lambda goes to infinity, this will reconstruct the densities, and the scaling is the correct one because I will put another 1 over lambda in front, so this will be 1 over lambda squared, and squared over lambda squared will give me rho 1, rho 2, okay, and it's what becomes. Again, he doesn't discuss about convergence because this is in 49, so convergence came around the 60s, but actually his calculation is correct. No, later we figured out that this is the right calculation to do, right? Of course, in dilute regimes, and it's surprising that as it is common in this modeling that these functionals are valid in the dilute regime, but people use them in order to predict phase transition. So actually, Onsager truncated it at the second order, and from that functional, he derived the nematic phase transition and other interesting phenomena for a functional which is not valid in the phase transition regime, but it's rich enough to predict it. So this is very common in this research. Okay, so this was so let me just say a couple of remarks for that. So we believe that this calculation can be done now rigorously using this result here for one species, for finitely many species is is okay. So let's say rigorous derivation of Onsager's functional following this, and in fact you can extend it to countably many species. And today I would like to discuss about uncountably many. So the full case where you have continuous orientation, not just discrete. So actually it is not difficult to do it for countably many species. And this without thinking of Onsager, we proved with Jansen, Tate, Welshi, and myself in 2014. Even before knowing these results of Onsager, it was for us an interesting problem to study after this one. And this is true for countably many, but countably many, maybe we cannot do it directly in the canonical, because how I would write a canonical ensemble for countably many species when n is fixed, right? So it's not so convenient, so I would do it through the grand canonical, so I would do it for this, right? I would work in the grand canonical and invert and do this trick. So actually what is in that paper is essentially that what is true here by Lebowitz and Penrose for one species is also true for countably many species. So not very surprising. There are some delicate points. People who maybe from chemistry that have worked with mixtures know that there are some surprises and things are not so smooth. But okay, so thank you. And what I would like to discuss today is about the uncountable case. So uncountably many species. And this is a natural thing to do, because actually for the Onsager functional, you don't want to have the discretized version, maybe you want to have the continuous version. And in fact, this is formula 25 in the paper of Onsager. Then formula 27 is the uncountable case. So he says, yes, okay, so this is a good discretization, I can control it, and I can pass to the limit, and instead of having the sum, this become integrals. Okay, of the density for the species K1, the density of the species K2, and now this becomes an integral instead of so the orientations. And I integrate over the angles. Okay, so as in the functional of liquid crystals. Okay. So the fourth remark is that there is nothing new. This all that was very well known in liquid state theory. So in liquid state theory, there were a huge amount of work around the 60s, and in particular in the works by the Dimitrios, Tsagkarogiannis, and Morita, a series of papers, and George Stell, where they have all these graphical expansions of any kind of thermodynamic quantity you would imagine with respect to any other thermodynamic quantity you like. So the free energy with respect to the density, the free energy with respect to the two-point correlation function, the two-point correlation function with respect to whatever you like. So these are in these papers, and this is now standard material if you want in liquid state theory and in textbooks. So this is somehow textbook material in a textbook like Hansen and McDonald in liquid state theory, with the only difference that we don't know whether these are convergent. So all these expansions algebraically are correct, but we don't know convergence, so we don't know this. Okay, of course for the Virial we know, it has been approved, but for all the rest, this is unknown, and the problem is that all these are based on summary summations, and the summations in mathematics are exchange of sums, and exchange of sums might be dangerous. Okay, so, and this is what we wanted to do, right? So we wanted somehow to revisit these words and using the previous knowledge on these techniques to show that to what extent these are rigorous. Okay, but as far as the formulas are concerned, they are here. So you go and you take Hans and MacDonald and you find them, and also other books. But I'm saying that because this is one of the most common. No? So formulas are here. And it's not only a mathematical, let's say, problem to look for convergence. It might be that you understand better the structure and you might find better expansions. And maybe you understand better the combinatorial structure, and this allows you to see other quantities to consider and things like that. So it's not only a technical point. I think it is an essential point to understand the convergence of this series. Of course, again, I'm always saying that because it should be clear. Even though these are expansions valid for the liquid state theory, and with closures which have been checked that they are valid in liquid state theory, rigorously are valid only the gas regime. So if you want to check the convergence is always in the gas regime. It's not after the transition point, even though they have been successfully used here after some closures, but they have not been studied rigorously. They have been studied experimentally and with simulations. So in that one has to be careful, and maybe there is some room of improvement in that applied research, knowing better what is the structure of these expansions. Or maybe, we have used them in order to suggest other numerical methods which might, work faster for the computer. Getting, let's say, more the next term of this convergence series, and this makes more accurate simulation. Okay, so good. All right, so this is the point, and I will try now to say a couple of words, even though I showed more or less what is happening, of the uncountable case, and how we do this inversion in the uncountable case. So I have to rewrite the partition function in the uncountable case. So instead of having now just one activity, I have a measure, right? Or a function if you want. So I rewrite now the partition function in a slightly different way, which is the same as before, with the only difference that activities are measures. So e to the minus some v xi xj of qi qj, so qi qj. This is sum over I and j from 1 to n, and this is the sum over n from bigger than 1. And then I have z to the n, which is now a measure on q. So this is the only difference with before. I can realize this measure by putting an external field. This is very common in inhomogeneous systems. Also in physical literature, people put an external field for this activity in order to make it vary in the domain. So this is not constant anymore, as it was before, but it is a function, or if you want a measure. I have an integral. I put the integral. Thank you. Okay, so I'm going to do exactly what I did before. Now, the only difference is that when I take the density, I have to look at the Radonico-Dean derivative with respect to this measure. Before I was taking a derivative, rho was the derivative of log xi, and now it is going to be the Radonico-Dean derivative with respect to that measure. So rho lambda is going to be a new measure. Again, here the density will be a density of inhomogeneous systems. It will be a measure on the space. And this measure is again the derivative with respect to z, but in the functional space, because z is a function, or a measure if you want. And it has exactly the same form, but written in this way, which is a way to express the Radonico-Dean derivative of this measure with respect to that measure. Okay. So the only thing that changes, people in functional analysis could immediately say, yes, okay, we know how to do that. We have a power series in Z. I want to write a power series in row. I have a mapping from one Banach space to another Banach space. There are some general theorems whether the inverse exists. This is true, and this is applicable here, and in fact you can do that. With the only difference that one, you get a radius of convergence which is slightly worse than what we have, and second, it is not valid in systems that grow. So if I have a shape of molecules that grow, there are some counterexamples. So what I'm going to show is a bit more general. But conceptually, for analysts, mapping from a Banach space to another Banach space, there are some theorems that say that the inverse exists, and yes, you can apply it here and get the result in some cases, in most cases. Okay, so what we want to do is to invert. We want to write Z with respect to rho and repeat exactly what I did before. Okay, so the proof goes as follows. So what I have to do is I have to compute that. So I need to take the functional derivative acting in one of these vectors. So this is Z1, Z of dq1, Z of dq2, Z of dq3. I fix one of them, I call it Q, and I take the functional derivative with respect to one of them. So since this is linear, taking the functional derivative is like removing it. Right? So I fix that, and they integrate over all the others. So this that I remove, which is the qth one, I remove it, becomes a ghost in this terminology. So I just need to repeat this sum with one fixed. And this is what this derivative will be. Okay. So it's exactly the same. And actually, the Mayer trick of doing the product of 1 plus f is exactly the same, because if I do it for all particles, or if I do it for all particles with one fixed, it's the same thing, because this one fixed, if I have all particles, I can take one and say I fix it somewhere in the volume, and all the others depend on that one. So it's the same thing. So it just give me a volume in front. Okay, so if x1 is exactly the same. And this is just to say that I can write it as the logarithm of that. Think in the same way that I get exponential before. So there is a function that I call it A, which depends on this root, Q, and depends on this measure, zeta. And this can be written like that, because I apply Mayer's trick here, in exactly the same way. Okay. Good. So I have rho equals z times e to a function of q comma z. Actually, this function I can write it down. Maybe I do write it down because it helps for understanding. It's exactly what I said before. I just need to fix one particle. So A, Q, and Z is written is the sum over n bigger or equal than 1 over n factorial, the integral of another function a n. I write it like this, and then I say what is a n? Q, Qx1 xn, and the integrals are over xn, zn dx. Now I call x the variable of integration and q the fixed one, where an is what I said, I fixed one particle. So this is the product of, I have fixed one particle, and then this might have many links to the remaining particles. So this can be written as f of 1 q xi I from 1 to n minus 1. So this is the product. So the product of 1 plus f will give me 1s, but the 1 will cancel with this one. So it will have a 1f or 2f's or 3f's. And see, this says which particle is attached to the fixed one. Okay, so I might have 1, 2, 3 attached. So this is what this product says, and the rest is the same. So the rest is going to be the sum over the connected graphs on the remaining particles. Product of f. So this is what an is. Okay, and this is what I have in the system. And now I want to invert it, and I have 3 minutes to conclude or not?
Well,
1 minute? 1 minute. So I just showed the inversion and I stopped. So what was the trick? I should bring it up? No, I should not move this one. No, yes, I can't move the other one. So I conclude, yeah, in 1 minute. So I have I have rho equals z e to the a q of z. So the trick is the following. Let me call t, depending on the root of rho. I define this to be e to the a of q of z. So if I define that, then I find that I have the following formula. Rho dq is equal to z dq times t, because e to the a, I call it t of rho. But this is also equal to z e to the a q. And then instead of z, I replace rho times e. But e is t. So rho times t q rho. So I have that here, so I have a formula. So I have that dq is equal to e to the a of rho, dq of rho is e to the a q fixed rho t q. So I have a algebraic equation for this option. And with this I conclude. So we have that this now, what is t, is a power series. I have a explicitly, it's here, so I can expand it, and I can expand the exponential. So in principle, by plugging in something here, let's say this is a power series, and I want to find the coefficients. So I put a power series here, I put a power series here, and I equate the coefficients, and I find it. And I can find that there is a unique solution because it has a triangular form. So the coefficient is calculated uniquely from the previous one. So I can find what this t is. So this has a solution, and it has also, I can also prove that it is convergent, because a power series that I can compute uniquely, and I know that it is convergent. So I found it, and I know that it is convergent. So this is the inverse, because if I know t, I know rho with z with respect to rho, because t depends on rho. So this was what allowed me to make the inversion. Okay. Now, the interesting thing is that this t has a very interesting combinatorial structure, and it's actually the generating function of some special trees, which is, if you think, it works like a key, because if I take now these trees and I compose them with A, these are the coefficients of the expansion I want to have with respect to rho. Okay. So I think I stop here, and thank you for your patience.
Thank you. Any last questions which can be answered in 10 seconds?
I have one complicated one real fast. So if you think of Onsager expansion, so
Yes.
when you think of rigorously proving its convergence, is there an estimate on the radius of convergence?
Yes.
So what is it, do you know?
Yes, exactly. So actually from here we get an estimate, which is like the Lebowitz Penrose. And actually if we use this new technique, so this is similar to Lebowitz Penrose, not similar, it's a different, completely different technique, but it gives a similar result for the inhomogeneous case, for the continuous case. Okay? So, and this technique gives like 30% better radius of convergence than the Lebowitz Penrose. And calculating that, I get a radius of convergence which is 30% better than the Lebowitz Penrose, and this is the radius of convergence for Onsager's function.
All right, so let's thank Dimitrios again, first of all.